Okay, so that's the story of constant and constant. Okay, let's go on to example C, shall we? Oh, they're just third horse.
It's Andrew and his sister Janine.
We're fine.
Lucky doesn't know always.
Okay,
Inside out.
now let's do the antiderivative of this. Now, guess what? This is just like back in the old days when we did derivatives. Remember we had to rewrite it first?
Yeah. Or
Okay, we're not ready yet, but if you
X
rewrite
to
it,
the 1/2.
let's rewrite this as 4x to the 1/2 power so that it's in not radical form, but what form?
Exponential.
Exponential form, and now it's ready for our little antiderivative experiment. Okay? So, the antiderivative would simply be, okay, what's the rule?
Add
Add 1.
Add 1 to the power,
Divide by something.
divide by the
New exponent.
new exponent, that's right. Okay. Just like that. All right, what about 2x? That would be 2x
To the second.
to the, that's first, so it's second now, over the new power of 2. We're losing it. We're gonna lose some time. Okay, we're losing time.
Understood this message.
Okay,
It
now,
was good knowing.
4x, now if you add 1 to 1/2, what happens? 3 halves divided by, oh, we're going to have to reciprocate, right? I tell you, Agent Roberts is sharp today. Very sharp. Okay, so get ready to reciprocate.
Be the best.
Now, now look at 7. This is interesting. This is a new one.
7x.
Whose derivative is 7?
7x.
7x, good. Now, if you want to do it this way, yeah, you can actually make it 7x to the what?
0.
0, which goes to 7x to the first over 1. So it works, doesn't it? Okay. Or you just remember, okay, whose derivative is a constant? Oh, constant x, right? Got it. All right. You don't need a plus c because it says antiderivative. That's just strictly backwards. Don't worry about the constant. Okay. All right. So let's make some sense out of this mess. Final answer would be 5/4 x to the 4th. You can scoot the 5/4 as a coefficient if you want. I like that better, but if you want to leave it together, that's okay. This cancels nicely. Oh yeah, wait a minute. Isn't the derivative of x squared 2x? Oh yeah, you could have actually done that one in your head, couldn't you, right? All right. Now reciprocate, and that becomes what? 8/3. If you really want to impress which way that, could you change 3/2 back into cube and square root? All right. Back to radical form where it came from. Okay, it won't count off, but it was nice. And plus 7. There you go. And now remember, what I'm doing is I'm giving you the derivative, so I'm actually giving you the what? What is derivative again? Derivative is always slope, yeah. Let's isolate this one example. Look at this right here. If you just had 7x all by itself, what does y equals 7x look like on a graph? It's a line. What is the derivative or steepness of 7x at all times? It is constantly 7. It never changes. The slope does not vary as in variables, right? We're going to varying slopes, okay? It's a constant slope. So each one of these is just the slope of the original one. Okay? There we go. All right. Now let's check out D, which will be very similar, except we have some x's in the denominator now. Careful.
You don't hide the maze.
All right. Okay, now let's check out the next one here. And what's happening here? All right. That's true. Didn't worse. All right, now, in example D, we're going to do some integration. All right. Kind of, yeah, it kind of is actually. Don't worry about that. If Dr. Looney is watching this, welcome to our AP Calculus class. All right, we're reviewing for the AP exam right now. Okay, all right. I'm about to integrate the three of you into the office.
Oh. I get to stay on the front row.
You're borderline already, okay.
Just like
Now,
growing or something.
I don't know, just focus. All right, now, okay, 15 minus. Now, right here, you have to rewrite this. The biggest mistake that students make, they take that 3 and they drag it up to the top. But wouldn't 2 times 3 be 6? Now, since when is 6 equal to 2/3?
It's not.
That's not, no, you can't do that. Don't you have to leave 2/3, 2/3? But only take the x, and the x becomes what? X to the -7. And keep the 11, but only take the square root of x, and it becomes x to the -1/2. There you go. Okay? So do your rewrite first. Now, it's just as simple as following the opposite of the power rule, basically. Okay? There's no name for it, but it is called integration, and integration is the same thing as antiderivative. Okay? Except for with the constant, right? Okay. All right. Whose derivative is 15? 15x, right? Okay. Wonder whose derivative is this? Well, let's think about this now. It would be -2/3 x to the new power of 1. If you go up by 1, it's -1.
All over 1.
Divided by that new -1, right? Okay. All right. So far, so good. Agents, flowers, and rye batter? Yes.
I wasn't it.
All right.
Welcome to this.
Are you? Not for long. Now, 11x to the -1/2 becomes 11x to the positive 1/2 over 1/2 plus c for the history constant that could have been there but disappeared when you took the derivative, right? Okay, could be. All right, so let's finish it up. Final answer: 15x. What does this become?
2/3.
Positive. 2/3, but put the x back down. Very good. So the x will be down here. Okay. And this will become plus 22. Very good. Reciprocate. And you want to impress Mr. Wade, put it back into radical x instead of x to the 1/2, right? Okay. And then plus c. Here you go. Now you can actually do some handcrafting of problems like Mr. Wade does. Foil, integrate, and there you have a handcrafted problem, just like that. Very nice. All right. Yes, question, Kevin?
Wouldn't integration help you, like earlier when we were trying to figure out like the area of the parabola? Or
Oh, good memory. Wow. Let's keep that.
Would that-
Very good memory. More like. Chris, you remembered it, you applied it. Very nice.
Lucky guy.
All right.
It's like.
Yes, you may recall when we were doing the area of the curve, remember that? And didn't we draw a bunch of rectangles? It's like, okay, let me draw 5 rectangles. Yeah, that'll be a good approximation. All right, good enough for what we did. And then integration gives you the exact area of a shape, and that's one of the most useful real-life things that we have. Okay? For instance, okay, future engineers. I'm sure we have future engineers in every class. Okay, we actually produce a lot of engineers at Page High School. All right. You got to make some kind of airplane part, and airplane parts are made out of volume, which is integration actually. And you got to figure out exactly the size of that part. Okay? Because if you miss it on an airplane, you're in trouble. All right?
Was the mathematician Archimedes?
Yes, Archimedes.
Archimedes. I did the project
Was,
with him.
yeah, he was the one who figured out. Well, they think he probably figured out the infinite rectangle
Yeah.
integration before anybody else did.
And
And they actually didn't even know it until 1998 when they figured out that they found some old papers.
I thought it was cool. It's like a thing you had for flip ships.
Oh, yeah.
It was way
Because I'm
back.
feeling like crazy, isn't it?
Integration to get 3
Was that?
like a triple integration.
You could.
12 minutes.
Okay, you're good. Okay.
No, I
All
get you.
right. Now I want you to put on. Thank you, Adam. I want you to put on. Stephanie. I want you to put on your thinking cap for this one. Okay. This one's a little deeper discussion here. Very interesting. Very interesting. No, not yet. Not yet. Okay. Very interesting discussion here, actually. No. It's not exactly. It's close, but it's not exactly. Okay. Might surprise you. Okay, we're gonna find the antiderivative of 1 over x, which is the same thing as asking the question, what function's slope is measured by 1 over x, because that's what we're looking for, right? Okay, so whose slope is exactly 1 over x at every single coordinate, it's 1 over x.
There's
Okay.
none.
Well, close, but it's not exactly right though. There's a little twist, okay? All right, here's how we're going to explore, wait. Sorry, well, what?
Because it makes
How it works out.
zero.
Okay, you already worked it out? Okay, good. Very good. All right, now, okay, let's see. Let's tell you what, let's write this down first, before we put how to do it. Let's put down how not to do it, okay?
Don't bring it up to the top.
Don't do this, all right? 1 over x is the same thing as what?
So now it's x to the negative 1.
Isn't that just x to the negative 1? It's tempting to go back and say, well, we learned this whole antiderivative rule today. So why don't I just add 1 to the power?
Then it's
If you
1.
added 1 to the power, it would be x to the 0 over the new power of 0. See why that doesn't work?
That's why I said it would.
Okay? That's no good, right? So what you get, it does not exist. Now, I'm sure some function has a derivative that is 1 over x because we discussed it this year, so it can't be, does not exist. So this one is an exception to the rule. It's the one that doesn't work with the rule. Okay? So, because the negative 1 doesn't work with the rule, I have something better for you. All right? Whose derivative did we do this year that always turns out to be 1 over x? Let's start with that. Isn't the derivative of natural log of x
1 over x.
1 over x? Because it's 1 over the base times the chain rule of the base is? Times 1. So it works, doesn't it? Okay? But there's a trick though. The derivative of natural log is 1 over x, that's true. But the integration of 1 over x is not exactly natural log of x though. Okay? There's a little something to adjust here. Okay, let me show you why. All right, the best way to tell you this is to go over here and let's label this number line y prime. Let's actually do a derivative test and see what we're looking at here. We already have the derivative. It's right here. Okay? So on that derivative, are there any critical numbers?
No.
Is there any place that 1 over x could equal 0?
No.
The only time a fraction equals 0 is when the numerator equals 0, and that's impossible. But, just as important, it does not exist at x equals 0, and we have to plot those as well, right? So let's plot a 0, plot a d&e right there. And then when you do a first derivative test, don't you just pick sample points? Okay? So pick a number below 0 and do 1 over that. Isn't everything below 0 negative?
Yep.
And 1 over that would also be
Negative.
negative?
Anything above is positive.
Anything above is positive, what's 1 over positive?
Really small.
So here's your derivative test. I'm looking for a function that is that right there. Wait a minute. If y prime is negative, what is the original function doing?
Coming down, decreasing.
Y is decreasing. If y prime is positive, what do we know about the original function? So I need a function that is decreased, does not exist, increase. Well, here's the problem, it's the d&e. Okay?
There's a hole in my curve.
Well, now wait, it's not a hole, but you're close. You're close enough. Okay? Isn't 1 over x a perfect slope for natural log of x? It has something to do with natural log of x for sure. But here's the thing, isn't the natural log of x only increasing? Oh, we've done it many times, right? Doesn't the natural log of x kind of look like